Let's talk about this true or false question, because this was on the quiz. So I just wanted to briefly mention it because some people were way off. Some people looked at the theorem and said, oh, U cross V is equal to 0. Well, that's not true. U cross V might be equal to 0, but only if U and V are scalar multiples of each other, or if one of them is the 0 vector, but that's not given here. That you have to prove this is true universally, not just, oh, it works for, so someone actually picked some values for U and some values for V and did all the work and showed this was true for that particular specific example. That's not a proof. In mathematics, when you're proving something is true universally or generically, you have to prove it's true for everything. So just picking some numbers and plugging them in and then showing it's true for one specific case will not work. Now, if you're trying to prove something is false, it is a valid way to show something is false by giving a counter example where you actually show, hey, for these values and so on, take a look-see here. This is showing the statement is not true. But here, the answer was true. And so there were two things that I wanted you to say in order to prove it's true. First of all, U cross V, that's a single vector, by the way. Some of you were referring to U cross V as if it were more than one vector. That is a vector. And it's not just any vector. It is a vector that is, by definition, orthogonal to U and to V, to both. So let me show you the picture again in case you forgot what the picture looked like. And in your lecture notes, I would encourage you to even turn to this page, which is the beginning of section 13.4, where I have the right-hand rule. See the picture of the person's hand here? Here is the U cross V vector pointing up in the direction of the person's thumb. And notice it is making a 90-degree angle with the U and the V vector down here, which you can think of as being in some plane, okay? So it's not that U cross V is equaling the 0 vector here at all. It's equaling a vector, non-zero vector, and it's orthogonal to the vectors U and V. So I wanted you to say that, and then part two of telling me that this was indeed a true statement is when two vectors are orthogonal with each other, there's this other really cool thing that's always true, and that is their dot product will be 0. So, and two vectors that are orthogonal to each other will have a dot product of 0. Okay? And if you said those things somehow in your own words or whatever, doesn't have to be exactly what I'm saying here, but in so many words, and I kind of got the gist of what you were doing and saying, then you got full credit, okay? But what I saw on some of the things on the quiz was not quite there, okay? So please know that. And when you're doing a true false, it is the case where if something's true, you cite a theorem or you cite a definition. Don't just show one example because that's not showing something's true universally. If you're showing something is false, though, you are okay to give an explanation, of course, or a counterexample to explain why something is false. And yes, there's going to be true false on the midterm, and it could show up anywhere because that's, you know, it's certainly a valid way to test. And they are very conceptual type problems, I will admit. Okay, so what did we do last time? Last time we learned what a vector valued function is. It is a function that you feed a parameter of time, like a real number t. Usually time represents, you know, the parameter is time because often these vector valued functions are used to model motion. And so the function spits out, if you will, the range is a set of vectors. But when you graph a vector valued function, you don't really graph the set of vectors. You kind of erase all the vectors and you only keep their tips. and then you connect their tips. And so you get a curve, not a surface, you get a curve. And yes, we're going to be looking at both curves and surfaces in 2D and 3D in this course. So make sure you know the difference between curves and surfaces. A sphere is a surface and a plane is a surface. A line is an example of a vector valued function because you can think of a line as being a curve. Well, a line is straight. It doesn't have any curve. Okay, yeah, but we use that kind of vocabulary to describe lines. So I'm going to move on. We're going to do limits now. We did domains last time, so I encourage you to review that. It's an important concept. So what about limits? So how do you take a limit of a vector valued function? Well, it's actually pretty easy. You can do it for a 2D or a 3D. And when somebody says, hey, take the limit of R of t, a vector valued function, you're going to simply take the limits of the components individually. And if all of those individual component limits exist, boom, the limit overall will exist, and it will be a vector, a constant vector. That is a vector that has constants for its components. If even one of those components has a limit that does not exist, then you can even write the answer does not exist. Okay? So here's a picture of limits in the world of vector valued functions. You've got a curve here. Okay, here's the R of t vector. And let's say it does have a limit L. Let's say some constant vector L is over here. The difference between them approaches 0 as the time approaches that constant. You're taking a limit as time t approaches some value. And so this R of t will keep going and moving and moving and moving until it finally sits right on top of the limit. And this is sort of a picture of that as your t goes to a. Okay.
You said that's the vector RT?
Yeah, this is R of t right here. And then as you plug in your time values that are approaching the value a, and as so you are adjusting your R of t a little by little. So let's say a was 1, then you would have time. You might start with time equals 0.9. Then your next time would be 0.99. Then your next time would be 0.999. You see how time is getting closer and closer to the value of 1?
Yeah.
So that would have your R of t. Here would be R of 0.9. Then this would be R of 0.99. And this right here would be R of 0.999. And then this would be R evaluated at 1. But sometimes that doesn't, that may not be defined. Just like when you took calculus 1, the limit, the function may not actually be defined at that value, but the limit can still exist. Let's do some limit review. And I'm doing this as a benefit to you because this is not in your text, but as a favor to you, let's review these limit facts to make sure you're clear about limits, because it might have been a while since you did some limits. What is 0 divided by a number where the number isn't 0? Like C is 10. Like what's 0 over 10 equal?
0.
Yeah, good. So 0. What's infinity over a non-zero real number? Like infinity divided by 10 is really what?
Infinity?
Yeah. Now let's do a couple of logarithm limits that you should already kind of have in your back pocket, okay? Ln of infinity and ln of 0 coming in from the right. If you forgot either of these, you can always rederive them in the following way. Simply graph y equals ln of x, and then look at what happens when x tends to infinity or x gets really, really large. What is this graph doing? It's approaching what?
Infinity.
So ln of infinity is infinity. Now, what about ln of 0? So as x gets really close to 0 from the right, what is the graph doing?
Negative infinity?
Yes. Good. So those are some logarithm limit facts for you. All right, keep going. What's 1 divided by infinity equal? Keep in mind infinity, if you know, good. Yeah, that could be like 1 divided by 2 billion. Well, it's a tiny number, approaches 0. Okay, now let's look at some exponentials. If you forget any exponentials, I encourage you to graph e to the x. You know that kind of graph from your days of pre-calc and so on. So e to the x would look like that. What's e to the negative infinity? So as x approaches negative infinity, x goes that way. What is this graph approaching?
0.
And a to the negative infinity will also approach 0 if a is some base larger than 1. What about e to the infinity? So as x gets very, very large, what is e to the x doing?
Infinity.
Now this one's weird. What's 1 divided by 0?
Completely undefined.
It is undefined, but we're going to say it's equal to infinity. Because 1 divided by a really, really, really tiny number goes to infinity. And then negative 1 over 0 is negative infinity. This one's also 0, by the way. How about cosine or sine of infinity? I mean, if you graph sine, it kind of rocks back and forth between 1 and negative 1. So as x goes to infinity, is there a limit to sine?
Undefined.
Yes, and we say dne, the limit does not exist because it's oscillating between 1 and negative 1. Now, here's the tricky part. A lot of students get number 9, no problem, but then they confuse that with number 10, which is a different kind of issue. What if you're putting a cosine or a sine in a numerator? You have x going to infinity, but the denominator goes to infinity. So because even though the cosine of infinity, that limit essentially does not exist, okay. However, this limit will exist because the numerator is really just jumping back and forth between 1 and negative 1, but the denominator is growing very large. And so the answer is 0. The limit exists. And similarly for sine, because that numerator gets basically killed off by the growth of the denominator. Okay, now let's do arctan.
Professor, really quick, on a to the infinite power, is that saying it equals 0?
Oh, sorry, this should be infinity. Thank you. I was moving too fast. Thank you. Yeah, this should be the same as e to the infinity. My bad.
Okay, thank you.
Thank you. See, I was testing you. Let's talk about arctan. You studied arctan when you took Calc 2, and you're all graduates of Calc 2. Congrats. So does anybody remember any of these limits for arctan? Like, what is arctan of infinity? If I graph arctan, it's actually kind of a cool graph, believe it or not. And you may not be so aware of the look of it. But I claim as x gets very, very large, the graph does have a limit. It approaches a constant. It has a horizontal asymptote. Does anybody know what that horizontal asymptote is? Yep.
Is it pi?
Somebody put it in the chat. Yep, pi halves. That is, this horizontal line has the equation pi y equals pi halves. What about x approaching negative infinity? So x is going that way. The graph is getting really, really, really close to a constant because there is another horizontal asymptote. And that horizontal asymptote is negative pi halves. You're on a roll, Kayla. Congratulations. Yeah. And these are a couple limits that I do put on quizzes and exams. So please know. Now, do you
That's just
guys remember?
because, I'm sorry.
Yeah.
So that's just simply because the range So like if you just take the domain of like the tangent function,
Yeah.
isn't it pi half or negative pi halves of pi halves, but when you're taking the inverse or the arctan, so that just means the range is basically negative pi halves of pi halves, right? So that's why it's like that.
Hmm.
Okay.
Yeah, because it is an inverse, right?
Yeah. Okay, thank you.
Yeah, because when we were looking at tangent, well, the original tangent function doesn't pass the horizontal line test, so it's officially not 1-to-1. So you chop it off, you chop it away, and you only look at the portion of it where x lies between negative pi halves and positive pi halves, and then you can take an inverse. And so the domain of that portion of tangent is this, which becomes the range of arctan. Mm-hmm. Correct.
Thank you.
You guys remember L'Hopital's rule? Because that's still going to be in effect. Let's finish out my chart though. What about 0 divided by infinity? Anybody have an idea what the heck that is? 0 divided by infinity. I claim it's 0. You can put that one in your back pocket. How about infinity over 0? It's infinity. 0 to the infinity power. 0. 0 to the negative infinity. Infinity, because that's basically 1 over 0. Yeah. Infinity plus infinity. Infinity. Negative infinity minus infinity. Negative infinity. Now, I'll put a number 18 down, even though it's not in your course reader. What about infinity minus infinity? Does anybody remember what that might be?
Isn't it infinity?
It's actually undefined, and you have to go do some work. Well, I should say it may actually be a value. Could exist, but it may be 0, but don't assume it's 0, because these could be 2 different infinities. It's indeterminate. Do you guys remember studying indeterminate forms in Calc 2? I don't want to we're not going to really get into that too much here, so don't like freak out or anything, but it's kind of fun. I'm not going to test you over again on Calc 2 indeterminate forms. Yeah. Yeah, type 3 indeterminates. Kelvin, you're a good student, you remember. Okay, let's do a little bit of L'Hopital's, because you're allowed to use L'Hopital's if it's applicable. Remember, L'Hopital's, and I'm going to call it LH for short. If you get a limit after you do direct substitution, you get infinity over infinity, or negative infinity over infinity, or infinity over negative infinity, or anything like that, or 0 over 0, then you're allowed to apply L'Hopital's. And we'll look at an example of that. Okay? Take a look at letter A here. Take the limit of that vector valued function. Oh dear, that looks crazy, doesn't it? You're going to individually take the limit of each of these 3 components. Okay? So I'm just going to look at the limit as t approaches 1, because that's what it says there, of the first component. So I'm going to first use direct substitution. Okay, 1 squared plus 1 minus 2 all over 1 minus 1. I get 0 over 0. What does that mean? I can use L'Hopital's. So how do you apply L'Hopital's? Well, you're still going to take a limit. So still write the limit down. This one is t approaches 1. You're going to take the derivative of the numerator. You guys all know how to do derivatives. Yeah, that's calculus. So for this one, it's 2t plus 1. And you'll divide that by the derivative of the denominator, which I believe is 1 for this guy. And then use direct substitution. Okay. I get a 3. Is that the final answer? No. Save that for later. That's the first component's limit. Great. Let's do the second component, shall we? That logarithm there. What's the limit as t approaches 1 of ln of 2 minus t? Let's use direct substitution. What's ln of 2 minus 1?
ln1.
And that's equal to actually a nice number. Anybody know?
0.
Yeah. Save that for later. Let's take the limit of this last component. Okay, so limit as t approaches 1 of cos 3 pi t. Direct substitution says cos of 3 times pi times 1. What the heck is cosine of 3 pi? Anybody remember some trig?
It's just -1.
Yeah.
-1.
Good. Okay, now you're ready to give me the final answer. Your final answer is a vector. You better use these angular brackets if you're going to put it in component form. I like that, my favorite. And then you're going to go 3, 0, -1. Voila. That's the answer to letter A. Mhm. So let's do letter B, and then we'll look at letter C, and then we'll move on to derivatives and integrals. Right? So derivatives and integrals are coming up, folks. So that's one of the reasons why I want you to wrap up your quiz 0 tonight, because that's the last one there on integration, because you got to have strong calculus skills in this class. So for letter B here, I'm just looking at this first component only. I'm taking the limit this time as t approaches 0. And I use direct substitution. And oh boy, it looks like I'm going to get 0 over 0. Well, the good news is L'Hopital's, LH. So I'm still going to take a limit as t approaches 0. And I'm going to take the derivative of the numerator, which I believe is cos t -1. Does that look right? And I'll divide that by the derivative of t cubed, the denominator, which is 3t squared. And now I'll use direct substitution, see if this works. Uh-oh, cosine of 0, I believe, is 1, and then the numerator is 1 minus 1. Uh-oh, I get 0 over 0. Now what?
L'Hopital's again.
Yeah, keep doing L'Hopital's until hopefully something happens. So the derivative of cosine t -1 is what? Does anybody remember the derivative of cosine?
Negative sign.
Mm-hmm. And then the derivative of -1 is 0, so that's done. And then the derivative of 3t squared is 6t. All right, let's try direct substitution now. Oh man, are you kidding me? 0 over 0 again. Oh dear. All right, L'Hopital's again. I hope there's a light at the end of the tunnel here. Okay, the derivative of minus sine, I believe, is minus cos. The derivative of 6t is 6. Now let's use direct sub. Okay. Ah, finally, I get something other than 0 over 0. -1, 6. Okay, save that for later. Woo! Okay, take the limit as t approaches 0 of 3t, oops, the middle component now I'm doing, which is 3t over t -1. Let's use direct sub. Should I use L'Hopital's on this?
No.
No, this gives a result. What is 0 divided by -1?
0.
Yeah, it's just 0. Not trying to trick you, but some people go, oh, that's undefined. 0 in the numerator. Okay, so save this for later. Finally, we're going to do the last. Oh my dear, look at that crazy. I love these kind of problems. I call these a double whammy. Why is this a double whammy limit, and why do I love it so much? Well, because you have to know more than one limit just to complete that one limit. What? I know, right? So you're going to take the limit as t approaches 0, woo, of e to the t squared over, no, that's arctan, sorry. Well, let's just do, well, yeah, we'll do the arc. So arctan e to the t squared over 2t squared. Okay, so if you use direct sub, you're substituting in t equals 0. Okay, what's e to the 0 divided by 2 times 0 squared? Okay, so I get arctan of something. So use your limit facts. Well, first of all, what's e to the 0? Does anybody know what that equals?
1.
Yeah, so that's a 1. And then 2 times 0 is 0. What did we say 1 over 0 is?
Infinity.
Okay, so that's what goes in the parentheses. So now what's arctan of infinity? Go check your limit facts.
Pi over 2.
Great, so we finally have a final answer for letter B. So letter B answer is this lovely vector. I'm going to use brackets, -1/6, comma, 0, comma, pi halves. Boom, I'm done. Okay. Is some of these limit facts coming back to you guys okay? I hope. Is this worth it? So let's look at letter C, and then we'll wrap up limits. I purposely picked sort of hard problems just to try to cover all my bases. So for letter C, if we take the limit, this is limits at infinity now, of e to the negative t, using direct sub, I get e to the negative infinity. And look at your limit facts. What did we say e to the negative infinity's result was?
I believe it was this
0.
Mm-hmm. Okay, good. Save that for later. So the first component had a limit. Great. Let's look at the second component. We'll take the limit as t goes to infinity, negative t squared minus 2 all over 3t squared. Ooh, yeah. I'm trying to write too fast. So I'm going to do this one. I'm going to talk about this in two different ways. If you plug in infinity here, you'll have negative infinity squared minus 2 over 3 times infinity squared plus 5, which essentially gives you negative infinity over infinity. So what does that mean? You can use L'Hopital's, LH for short. And that's totally legal for you to just go ahead and use L'Hopital's. I'm going to skip L'Hopital's, and I'm going to let you skip it too because of the following reason. And you took calculus too. Do you remember growth rates?
Oh, yeah.
So if you look at this quotient, do you notice that you have a polynomial of degree 2 divided by another polynomial also of degree 2? So I claim the growth rates are the same. And when you have a polynomial of like degrees, a numerator and denominator, you can kind of skip doing your L'Hopital's. You can still do it if you want, but the answer is going to be the lead coefficient of the numerator's polynomial, which is -1, divided by the lead coefficient of the polynomial in the denominator, and that's a 3. So overall result is -1/3. Save that for later. You guys remember this at all?
Yeah.
Let's look at the last component and take its limit as t goes to infinity. And now this is infinity squared all over ln infinity, which is, basically infinity over infinity. And you can use L'Hopital's, that will work, but let's use growth rates. Growth rates say what? Who goes to infinity faster? The polynomial that's in the numerator or the logarithm in the denominator? Does anybody remember the hierarchy of growth rates?
polynomial.
Yeah, polynomial goes to infinity faster than logs. And since the polynomial is in the numerator, what does that mean that the overall limit is going to be?
Infinity.
So because this component blows up, the final answer for part C is this vector valued function's limit does not exist because one of the components blew out. And we're done. That's right. Does not exist. Sorry. And now some memes.
So question. So there'll be no vector for this, right? Since we
That's
have an
correct.
infinity.
Nothing.
Okay.
0. Can't do a vector. It blew out. Yeah. Okay, after explaining this to my students several times, wanted to check she really understood it, gave her another example. Put the 5 on the side, you get it? All right, never mind. Okay, it's time for the exciting derivatives and integrals. And if you feel comfortable with derivatives and integrals, this part is going to be pretty straightforward for you. That's really good news. There's a little extra you kind of have to know when you're dealing with derivatives and integrals with vector valued functions, and I'll cover that as we go, okay? You do have to have strong derivative and integration skills in this class, and I can't stress that enough. And I kind of get happy that we cover it early in the semester because it's September right now. We will be revisiting derivatives and integrals in sort of different conversations as the semester progresses. And the better you are at derivatives and integrals here in this module can only ensure that later on you will be okay doing derivatives and integrals within the context of a different module, okay? So if you feel a little rusty or you need a refresher, please review those worksheets I've put in Canvas. And you know, if you want, see me in office hours, I'll maybe give you some more, I'll cook up some more off the top of my head for you to do. But some things that I expect you to really know how to do for derivatives, you better know how to do that chain rule, the product rule, the quotient rule, how to take derivatives of exponentials, logs, all of that, and derivatives of arctan, for example. For integration, you have to know how to do U substitution, but U substitution on steroids. You know what I mean? Like U sub when it's appropriate, integration by parts, the arctan rule, how to take integrals involving exponentials and trig functions like sine, cosine, and so on. All of that. Yeah. Okay, let's do the definition of derivative for a vector valued function. And it does involve limits. That's why we cover limits first, because derivatives involve, the definition involves a limit. And if you're going to do the official definition of the r prime of t derivative, it involves taking a limit as delta t goes to 0 of r evaluated at t plus delta t minus rt over delta t for all t for which the limit exists, okay? So if r prime really exists, you can say that r is differentiable, and that's fine. Now, good news, we are not going to have to use the limit definition in this class in order to take limits of vector valued functions. So I won't have you do that. So good news there. I do want you to see why it all works out though. So let's fill in the blanks here. This is sort of the benefit to you. And if you're going to take higher levels of math, you'll thank me that I did this, because this is sort of a basic rundown of other stuff. So here's your vector valued function, and it's given to you in two different formats. One is the linear combination of the standard unit vectors I and j, okay, and then my favorite, component form. Okay, whatever. Now, if somebody says, hey, go get r prime, and you've got this limit definition, you're like, oh my gosh, what's that? Well, if you start writing it all out, you're really saying this r evaluated at t plus delta t, and I'll use the I and j stuff, would look like f t plus delta t I hat plus g evaluated at t plus delta t j hat. That would be the first guy, minus, there's a minus there, just the original r of t. So the original r of t is just f of t I hat plus g of t j hat. Okay, and then this is all divided by delta t. And now what? This looks like a hot mess. Now you're just going to rearrange things and combine terms. So I'm going to look at all the I hat terms and put them in one big old chunk. So I'm going to have something really large here. And then I'll take all the j hat terms and put them together. So f of t plus delta t minus f of t all over delta t. So I'm sort of distributing this delta t, if you will, over all of these things. I hat plus, and then combine all the j hat stuff, g evaluated at t plus delta t minus g of t all over delta t. And then you're allowed to distribute the limit over a sum. That's some property of limits. It's the linearity of limits that says, hey, take the limit of the first component, that's legal, and then add that to, because we just did these limits for vector valued functions, and we were allowed to take it on a component by component basis, totally legal. Then what? Well, this right here is the definition of, this is from Calc 1, of the derivative of f. This is a Calc 1 definition. So you can just go, well, that's just going to be f prime of t times I hat. And then this guy over here, that's the difference quotient where you take a limit. Also the definition of derivative, but it's the derivative of g. So this guy ends up being g prime of t times j hat. So that brings us to the final theorem, which says, and I'm doing it for both 2D and 3D, but it's essentially almost the same. If you've got your vector valued function and somebody says, hey, go give me the derivative of it, all you have to do is individually differentiate the components and then give that vector valued function. That's it. Yeah. Just individually take derivatives of each of the components and then stick it into a nice, oops, that's supposed to be a k hat, and you're done. And as long as you're strong taking derivatives, it should be not a problem. Now we'll do some derivative examples, and hopefully we'll, if you're a little rusty, hopefully we'll refresh some of your brain cells on derivatives. Okay, the picture of it looks like this. You've got r of t here, r of t plus delta t a little extra, and then as delta t goes to 0, this r of t plus delta t gets closer and closer and closer to the r of t, and r prime ends up being the tangent vector to the curve. And this is key. And we're going to use that fact in one of the problems today on the next page. And that is going to be a problem on your quiz this weekend. Hint, hint. Yeah, I'm telling you what's on the quiz. So there you go. Aren't you glad you're here? So let's find some derivatives, and then we're going to use this handy fact. Okay. So here's some vector valued functions. Oh my God, these look terrible. Yeah, I know. Well, the first one's not too bad. So if you take the derivative of 1 over t, how do you do that? Remember, we're taking the derivative, not the integral. The integral of 1 over t is ln of t, but I'm asking for the derivative. So what you may want to do first is rewrite it as t to the negative 1 power, and then take the derivative of t to the negative 1 using the power rule from Calc 1.
Oh, it's just negative. Okay, sorry.
Mm-hmm.
It's just
Yeah.
negative 1 over t squared, right?
Mm-hmm. So first I do the intermediate step, negative 1 t to the negative 2, right? You do negative 1, take away 1, and rewrite that with positive exponents, and then save that for later. What about if you took the derivative of ln of 2 minus t? So on ddt means take a derivative of, and then notation, you put brackets next to that. And then you say what you're taking the derivative of. This is correct notation. I just want to do an aside, because I will take away points for bad notation. Bad notation, and I've seen students even in Calc 3 do bad notation. They'll put the thing that they're going to take a derivative of, and then they'll put ddt to the right of it. No, we don't do that. That's meaningless nonsense. So please use appropriate notation, because you're all graduates of Calc 1 and Calc 2, you know, right? Whoa, not too far. So you're going to be taking the derivative of a logarithm. So hopefully you remember your chain rule. So the derivative of a logarithm is 1 over the argument, so in this case 1 over 2 minus t, times the derivative of the argument. So what is the derivative of 2 minus t with respect to t? And then you can multiply these together to make it look a little prettier. So let's save that for later. That's the chain rule for the log. Now you are taking the derivative of a cosine. So what is ddt? The derivative of cosine 3 pi t. Ooh, chain rule. I think you're going to have a negative sign. 3 pi t. But you have to multiply that by the derivative of 3 pi t. with respect to t, which I believe is 3 pi. And now to get full credit in my class, clean it up. I like your coefficients to go in front of any trig or exponentials or inverse trig functions, just so people who are reading it don't by accident think that that 3 pi is part of, oops, not, that was supposed to be sine, my bad, is not part of the argument of the sine. So here is that, and now you're able to put it together in one big old vector. So final answer for letter A is going to be this big old vector. The first component's -1 over t squared. Second component is -1 divided by 2 minus t. Last component is -3 pi sine 3 pi t. And that is the derivative. So that, and in fact, to make it look real pretty, if you really want to impress me, put r prime of t equals. So I know, and you know, that that is the derivative of the vector value function, which is itself a vector value function. Okay, now let's do letter B because it's pretty gross. I didn't leave myself any room. Let's do some chain rule. So let's look at this cos cubed. All right, you're going to take the derivative of a cos cubed. What I would do, just to make sure you don't screw up, and this is what I do so I don't screw up, is I rewrite it where I put the cubed outside. Because really, when you're going to apply the chain rule, that's the outer function that's going on of this composite function. Now take the derivative with respect to t of this. So you're going to use the general power rule first. So you're going to go 3 times cos of 2t to the second power times, this is why they call it a chain rule, you're chaining it all together, the derivative of cos, but that's negative sine 2t, times the derivative of the argument 2t, which is a 2. Now clean this up. This is a hot mess. I want the negative, the 3, and the 2 to all swing out in front. In fact, you should be multiplying those together to give me a -6 coefficient. And then you'll have a cos squared of 2t multiplied with sine of 2t. And we'll save that for later. That's the derivative of the first component. I know it's pretty gross. Now let's look at the ln, because this is pretty crazy. What some students do is, because they must like pain, is they actually try to apply the log rule right away and take this guy's derivative right now. No. Step 1 is, how about we use log properties to simplify this logarithm and rewrite it as the sum and difference of smaller logarithms, and then take the derivative of that term by term. So in other words, expand. So what are the log properties I expect you to know? Well, one of them is ln of AB can be rewritten as ln of A plus ln of B. Another one is ln of a quotient, A divided by B, can be rewritten as ln of A minus ln of B. Another one is ln of A to the nth power can be rewritten as n times ln of A. I hope you remember those 3 properties from an algebra or maybe a pre-calc class that you had, and we're going to use all that. So the first thing I'm going to notice is this is a quotient. So it's going to be written as ln of the numerator minus ln of the entire denominator. Are we done simplifying? No, you can go further. The first term cannot be simplified further because you cannot simplify logarithm of a sum any further. Leave it alone. The second logarithm, though, has a product in there, so you can rewrite this as a sum, but you have to be careful because this minus sign is going to have to affect the entire sum. So then I'll distribute the negatives. So I'm going to have ln of 1 plus t to the 5th minus ln t minus the last logarithm. Now the last logarithm, I'm going to do something intermediate step. I'm going to rewrite the radical as an exponent, raising it to the half, because I can go one more step now and expand this logarithm all the way completely. And am I done with this problem? Oh, heck no, we didn't take a derivative yet. Now take the derivative. All we did was make it look expanded. And the reason why you want to do the expansion is it's super easy to individually take the log, the derivatives of each of these logs. So the derivative of the first log is 1 over 1 plus t to the 5th times the derivative of 1 plus t to the 5th, which is 5t to the 4th, minus the derivative of the middle logarithm, that's simply 1 over t, minus 1/2 times 1 over the t squared minus 4 times the derivative of t squared minus 4.
Hey, Professor, is it the same question on the book? Because
Yeah, our numbers are different.
Are your numbers different? Oh, okay. Oh, I see. I changed it up, didn't I? Oh, yeah, I was doing something that I apologize. I was doing something like this. You guys have something else, don't you? I see it now. I see it now. I see the error of my ways. Okay, so I guess I did all that work for nothing. Oh, tears. Okay, yours, I would, what would I do to expand yours? I would have to, rewrite that radical as, excuse me a second, I'm just making a note to myself. I would rewrite that as to the 5th power. So I was doing a different problem. I apologize. So all of this is going to go by the wayside. That's actually harder than yours. Yikes. Okay, so start over. If you have ln the 5th power 6t plus 1 to the t squared plus 2, you want to expand that. And I would rewrite this 5th root as the whole thing to the 1/5. And then if I expand it, I would get 1/5 ln of the quotient. But then I could rewrite the quotient as a difference of logs, right? And then distribute your 1/5. Okay, I'm gonna need another page. I'm running into a serious mess here. Sometimes I tweak my notes and I forget to change my other notes to match. Okay, now we can take the derivative. Let's do that. So you're going to have 1/5 times 1 over the argument times the derivative of the argument for the first guy. And you'll do the same for the second log. Let's save that for later. Okay, now finally, tell me if this is what you have. Do you guys have this in your course reader? The last component, is it really t to the 4th plus e to the 7t?
Ours is 9t squared e to the negative 2t. I think you had it on the above.
Okay, so I had it, I changed it again. Okay. Oh, I know why I did that. Thank you. Okay, does anybody know how I'm going to get started here? How do you take the derivative of 9t squared e to the negative 2t? That looks pretty crazy, doesn't it?
is that like the product rule?
Mhm.
Product rule.
Very good. Yeah, so you got 9t squared e to the negative 2t. I'm going to use the product rule, which says if you have f times g, that product prime, you can go f prime g plus g prime f. That's the product rule right there. Memorize that, baby. Okay, so who's f and who's g? I'm going to call the 9t squared my f factor. And how about the exponential e to the negative 2t will be my g. So when I take the derivative of this with respect to t, using this handy product rule, f prime would be the derivative of 9t squared, which is pretty easy because you guys know your product rule, I hope, or your polynomial rule. That's 18t. Okay. And then you multiply that by g, so don't take the derivative of that guy yet. And then plus g prime taking the derivative of an exponential, the derivative of e to the u is e to the u times u prime. Maybe you remember that? So it's going to be e to the negative 2t times the derivative of negative 2t, which is negative 2. So that's g prime right there. And then we'll multiply that by f, but that's just the 9t squared. Clean this up a little bit. I don't require that you factor a common factor out. If you want to, that's fine. But I usually just want you to put your coefficients and your polynomial factors in front of exponentials, just to make it look a little prettier. Not much. Okay, and your final answer for this guy, which is like a nightmare. Oh, I see what I did in letter C. Is wow. Negative 6 cos squared 2t sine of 2t. Okay, and then the middle term was 6 over 5, 6t plus 1. I'm running out of room, huh? Oh, wow, this is nuts. Okay. I know that's pretty hellacious. Okay, I'm going to stop right there for this. I'll let you do letter C on your own. I think I started off the other log for you. I accidentally did that log. Okay, so moral of story: know how to do all your derivatives and take it term by term. You're fine.
I don't think we have letter C in the book as well.
Let's see that. So why care about finding r prime of t? Why do you, what's the application of finding the derivative of a vector valued function? Well, look, because of that key fact that the r prime of t, which is itself another vector valued function, when you graph him, he is tangent to the curve given by the original function. That's good to know, because you can use that to help you get stuff. So that's going to be used in the next example. And in this next example, I hope I have it. Yeah, okay, there we go. So they're graphing this r of t right here. So this r of t is kind of cool because it looks like this curve right here. The three-dimensional curve. It's very lovely. And they want us to find a set of parametric equations for a tangent line. Now, when you took Calculus 1, if you'll recall, this is just some Calculus 1 review. I hope you remember doing these kinds of problems where they gave you like, hey, here's the graph of y equals f of x, folks. Yay. And I'm going to give you a point right there. How about the point when x is 2? Just as, you know, silly example. And I'm going to draw a tangent line to the curve right there. Yay, tangent line. Are you able to find an equation for that tangent line? Does anybody remember doing this kind of problem in Calc 1? Everybody raise your hand. I'm going to go look at the participants now. Do one of your hand raise reactions. Hand raising. I got some peeps here with their hand raised. Yay, look at that. Yeah, some people are remembering. Maybe it's bringing some sad memories back. I don't know. You like your Calculus 1. You know, does anybody remember this? We've got quite a few hands up. Okay, so some of you are remembering the Calculus 1 days. Tangent line equations. Well, guess what? It's coming back. That's right. But now you're doing it in 3D. Okay, well, what of it? Well, in 3D, remember that one line requires a set of parametric equations. You learned that within this last week. So if you're going to find a line that's tangent to a curve here in 3D, you're certainly going to be interested in getting those parametric equations going. So when t equals 2 is what they're saying. Everything, sorry. When I use my erase tool, Microsoft Surface likes to just erase everything. Like, help. Okay. So when t equals 2, so that when you plug t equals 2 seconds into your r of t, you will get a point on the curve. So let's get the point on the curve first, because this is also going to be a point on our line. So what is r evaluated at 2? So you're just going to do direct substitution here, no big deal. Okay, and I get 4, 3. Is that right? 8. So that's a point on the curve, and I'm using angular brackets. It's like, well, I thought you said points are use parentheses. I did, but you can think of this position. You can then say, well, we only looked at the tips of the vectors. So the point 4, 3, 8 is a point on the curve. Okay. So if I graph where 4, 3, 8 is, so let's just say it's like way up here. Here's the point 4, 3, 8. Okay, fine. Now I'm going to try to draw a tangent line to this curve. I'm not real good at drawing straight lines, but hopefully you can appreciate. Well, that's really sad. Okay, that's supposed to be a straight line, folks. That's your tangent line to the curve. Okay. There he is. Now, in order to get the parametric equations for this tangent line, because here's our goal, get the parametric equations for this tangent line. Yep. Parametric equations for this line. Remember, we need 2 ingredients to get parametric equations for a line. One of the ingredients we got, a point on the line. Because this point that's on the curve is a point on our tangent line. So that 1 down and 1 to go. How do we get a direction vector for this line? Good news. Here is the claim. The derivative r prime is tangent to r of t at any point t. So r prime evaluated at 2 will give us the direction vector for our line. But we first have to get r prime of t. So first, get r prime of t. Once we get that guy, we'll be able to substitute t equals 2 seconds in there, and boom, we'll have our direction vector and we'll be able to complete the problem. Yay, success. So this is a real easy problem because r of t just has some easy polynomial components, and you guys know how to take derivatives of polynomials with no problem. So let's go get r prime here. So we're just going to take the derivative component by component. Easy peasy. The derivative of t squared, 2t. The derivative of the middle component, 2t minus 1, 2. And the derivative of the last component, t cubed, 3t squared. Now, evaluate that at the point when time t equals 2 seconds. You're just going to use direct sub. And I get a vector with components 4, 2, and 12. So now I need to finish out the problem. And so to finish out the problem, you are just going to get those parametric equations for the line. Let me remind you, in case you forgot, generically speaking, these parametric equations form a set, x equals y equals z equals. The coordinates of the point on the line, x naught, y naught, z naught, plus some number times the parameter t, where these are the direction numbers. Those are the components from your direction vector. So the final answer for us for this particular problem, we got the coordinates of our point. That was 4, 3, 8. So I'm just going to write those down quickly here. And then the rest of these equations using the components from our direction vector. So x is 4 plus 4t, y is equal to 3 plus 2t, and z is 8 plus 12t. And we're done. We got the tangent line. Congratulations, you just did something in 3D that you used to do in 2 dimensions when you took calculus 1. So let's burn through some weird properties with dot products. if you're taking a derivative of a constant, a scalar multiple with your vector valued function, it's what you'd expect. The scalar just multiplies through. If you're taking the derivative of the sum or difference of two vector valued functions, it's what you think. It'd be the sum or difference of the derivatives of those two guys. Now this one's weird. What if you take the product of a scalar function with a vector value function? This is not a dot product, people. This is not a dot product going on. All you do is you use the product rule, just like you learned from Calculus 1, and it would be WT times R prime of T plus W prime times R. Okay. Now, in number 4, we are looking at the derivative of a dot product. Ooh, what the heck? Product rule, R of T dot product with U prime plus R prime dot product with U. So we just use the product rule again and carry through the dot product. Ooh, derivative of a cross product. Can you do that? Sure. Product rule again, R of T, cross product with U prime, plus R prime, I can't write, cross product with U. A lot of product rule going on here. Product rule is super important. What if you have a composite of a vector valued function with a scalar function? Boy, that's wacky. We rarely do this, so don't get too worried about it. So you're gonna use the chain rule. You're gonna take the derivative of the outside layer, if you will, R prime of WT, and multiply that with W prime of T. Now here's a weird one. I'm just gonna put a little star by it because it's like, really, is that true? If you were taking the dot product of a vector valued function with itself, and this is a special case, and you get a constant. That doesn't always happen because sometimes you get like a function of T. Then what's true is R dot product with its derivative will give you 0. So in other words, he's going to be orthogonal to his tangent vector. Cool. I'm going to prove it. So let's say you're given that R dot R is equal to a constant. This is a dot product here. So let's say this is given, like this is already true. You know it to be true. You get that for free. So then what? If I take the derivative of the left-hand side, that better equal the derivative of the right-hand side since they are equal. Okay, let's do the right-hand side first. Does anybody remember from Calculus 1 what the derivative of a constant is? Like what's the derivative of 3?
0.
Good. Yeah. And the left-hand side, you're going to use this theorem here. In fact, we're going to use number 4. So we're going to use property 4 above here that says when you take the derivative of a dot product, using the product rule, you're going to have R dot R prime plus R prime dot R. But these are really like terms. So you're going to add them together. So the left-hand side, basically, because it doesn't matter what order you dot product things in, is really 2 of these dot products of R with R prime is equal to 0. But then if you divide both sides by 2, then the 2's cancel, and 0 divided by 2 is 0. And so boom, I just proved it. Pretty cool. Okay. End of proof. So we're going to just do a quick example here, and then I'm going to get into integration. So find the derivative of the dot product. Now, folks, there's 2 ways to do this problem. You could first do the dot product and then differentiate, or you can apply the product rule. So both ways are good, but let's just do this way because it'll be a little less involved because you're going to have to use the product rule somehow. So if I just look at R prime only, and we already went over how to take the derivative of 1 over t. Remember, it was negative 1 over t squared. And then the derivative of negative 1 is 0. And then the derivative of ln of t is 1 over t. And if I just take u prime by itself, I'm going to get 2t, negative 2, and 0. And then, of course, I run out of room. And now I'm going to put it all together using the product rule. So r prime dot product with u is going to be -1 over t squared times t squared plus 0 plus 1 over t times 1. And so I'll do a little bit of reducing here. The t squares cancel and I get that. So sort of save this for later. And then the other term is u prime dot product with r. So I'll do that. 2t times 1 over t plus -1 times -2 plus 0. The t's cancel here. I get 2 plus 2. Oh, that's nice. 2 plus 2 equals 4. Then when I go r prime dot product with u plus u prime dot product with r, I'm going to get -1 plus 1 over t plus 4. And then I can clean this up a little bit to get 3 plus 1 over t. And there's your final answer, and we're done. Little application there. Okay. Let's integrate. So this is an interesting tattoo of the fundamental theorem of calculus. You guys recognize the fundamental theorem of calculus?
It is very beautiful.
Yeah. It's a gorgeous tattoo, right? Mm-hmm. All right, now let's look at integrating a vector value function. Like, who cares? Well, you're going to care. So we're going to do a few different kinds of problems here. But first, let's just look at the definition. If somebody says, hey, go integrate a vector value function, what the heck? What do? You just integrate component by component. Just like if they ask you to take the derivative, you just take the derivative component by component and then stick it all together in one big old vector as your final answer. Okay? Is that all? Well, there's a little bit extra there. What's missing from this definition? Do you guys remember when you took an indefinite integral? That when you take an indefinite integral, you got a plus c? Does anybody remember that?
Yeah.
Good, because they're not showing you that here. So for the indefinite integral, this is the 2D version, they should put plus a constant vector, not just plus c, a constant vector. Okay. So if I really want to break it down, this would be like it'd be a 2D vector because this was an integration in 2D. So it'd be a vector with a couple of constants there. Well, what are those constants? Well, unless you are given extra information, initial condition, you don't know. And so also a 3D integration problem, you would have plus some constant vector. And notice I'm putting the little arrow over the c, not just plus c, because it's a vector. So this constant vector would be a vector with 3 components. Okay, that's missing from the indefinite. And you can make a definite integral too. Definite integral, you don't do a plus c. You would just have the limits there, and you would just take the definite integral of the 3 individual components. Okay, so what's missing is you got to do the plus c here. So let's do an easy peasy example with the plus c. Okay, this is an easy integration problem. So what is the integral of t with respect to t? You guys know how to do that?
T squared over 2.
Yeah. Plus c1. Integral of 3t plus c2. Integral of sine 2t. Uh-oh, you may have to do a little bit of u sub. U is 2t, du is 2 dt, so you need a 2. So what I do is I put one in and divide out. So this is going to look like 1/2 sine of u du. So that's going to be 1/2 negative cos u plus c3. And then replace the u with what we said it was, 2t. And then your final answer has to be a vector. So if you don't give me a vector, your final answer, oops. So one way you could write your final answer is put all the constants in your answer. So t squared over 2 plus some constant c1, comma 3t plus c2, comma -1/2 cos 2t plus c3. That's a perfectly legit answer. MyLab Math may want you to rewrite it where you pull the constants out and you don't stick them in your, so you're gonna do plus, you know, C1, C2, C3. And then further, they may just want you to replace this vector C1, C2, C3 with a big old C. You know, it's a vector, so I'm using vector notation like that. Okay, so either of these answers is okay with me, just so long as you acknowledge that you have that constant vector somehow. Okay, so I'm done with indefinite for now. What about a definite integral? Let's look at a definite integral. How do you do one of those? Well, you know, carefully. So do it component by component. This is just review. You've seen this kind of stuff in a Calc 1 course, I'm sure. When I integrate cube roots or any kind of roots, I always rewrite it with exponents and use my power rule. I encourage you to do that. So when you do this, you're going to add 1 to the exponent and you divide out by 1 to the plus 1, right? And then you'll evaluate at the limits. This is going to look like 3/4 t to the 4/3. And if you evaluate between those limits, so I put brackets over here on the right and I go 0 to 1. That's very classic notation. Please do not put the bracket over here on the left and do your limits. If I see that, even if your final answer is correct, I will be docking you bad notation points. Yes, it matters. You graduate from my class, you gotta have good clean notation. So when I substitute a 1 minus, then I substitute the lower limit of 0. Well, 0 to 4/3 is 0. Final answer for the first component is 3/4. Save that for later. Let's do the middle component. How do you take the derivative of 1 over t plus 1? This is the log rule in action. Remember the log rule? I'm going to use u sub. Let u be t plus 1. du is just 1 dt. So this is looking like the integral of 1 over u du. That's going to be ln of u. But that's really ln of t plus 1, absolute value of, and then evaluate between 0 to 1. So plug in your upper limit first. So you're going to have ln of 1 plus 1 minus, then evaluate at your lower limit. I get ln of 2 minus ln of 1, but ln of 1 is a nice number. What is it? Quit.
0.
Yeah, so kill it. ln 2, save this for later. Okay, last one. How do you take the integral of an exponential, e to the negative 3t? You recall that the integral of e to the u is e to the u. Okay, so if you use u sub here, where your u is negative 3t, your du is negative 3. And I don't solve for, I know some of you took your calc, the way I do it is I put in the missing factor, but then I divide out by that factor. That's essentially multiplying everything by 1. So now this looks like negative 1/3 to the u du. Cool. So you'll get negative 1/30 to the u, but then u is negative 3t, and you'll evaluate this exponential between the limits. Plug in that upper limit first, minus, then plug in the lower limit. And this is a minus minus, so you can change that to a plus. What is e to the 0?
1.
1.
Okay, and we're done with this. And so the final answer for this definite integral, yes, do I have the answer? Did I put the answer anywhere? No, I did not. I thought I did. Okay, so this final answer is kind of gross. Big old vector, 3/4, comma ln2, comma negative 1/3 e to the negative 3 plus 1/3. Yep, I know that's a pretty gross answer, but there you go. All right, definite integrals. I'm going to skip this one. If you want to see it done, watch my video. Okay, I got a meme. But I want to do a particular solution one. Oh, do I not have one? Are we missing a page? I hope not. 14.
What is it missing?
No, here it is. I wrote over it. Example 7. I want to do example 7 for you. Okay. The other one's going to take me too long. A lot of use sub and integration by parts and all sorts of fun stuff that I love, but I may do a piece of it, but I'd rather do this one first because this is similar to what's going to be on your quiz this weekend. Aha, got your attention. Yeah, this one right here, example 7. Yeah, and so you want to care about this one. And it's the particular solution thing because this is actually very relevant, and you'll see why when we get into projectile motion and stuff like that next week. Okay, so what of it? Well, it's an integration problem, but more importantly, it's a differential equation. Oh boy. So this is a differential equation. Oh no, does that mean we have to go take Math 253? No, you don't have to do that, but that is a good course, Math 253, differential equations. So you have to work backwards here because they're giving you a derivative. They're giving you the derivative. And they're saying, okay, find the antiderivative of that satisfies this initial condition. So you saw these kinds of problems in Calc 1 and Calc 2, believe it or not, where they gave you a derivative and they gave you a little extra information. And the extra information is what you use to get the constants of integration. You don't plug that in right away. Like, don't use that extra info initial condition right now. No, you want to wait. Okay. So the idea is you're given a derivative, you go get the original function. So you have to integrate. Yeah, 3 times. So let's go do that on a different page because I don't have any room. Okay. So the first component in that derivative that they gave me was 1 over t squared plus 1. So I'm going to integrate that. dt. So I claim you're going to use the arctan rule, which I hope you remember because I feel that's very important, and you'll see that come up a lot in my class. Okay. So it turns out that, oh, no, I don't want to go to settings. So u is t, du is dt, and a is 1. So what am I saying? So if you have the look, here's the arctan rule of this, you can be assured that this is going to give you 1 over a arctan of u over a plus c. Hopefully you learn that in a Calc 2 class somewhere, somehow. So this one is simply going to be, since a is 1, this is just going to be arctan. For us, u over a is just arctan t. But you're going to have a constant of integration, so put C1 there. So save this for later. The next component, not too bad, you're going to take the integral of -2 sine t. That's easy. I claim that's going to be +2 cos, but you have a constant. Now, please use different subscripts because this constant of integration might be different from the other guy, the C1. So you better put a different subscript. That's why I'm saying C2. And yes, notation matters. If you accidentally use the same subscripts on your handwritten work, you miss a point. And then finally, let's integrate that last component. The integral of cos 3t u is 3t, du is 3. Put a 3 in there, divide out. So using u sub, the intermediate step. And yes, I like to see all these u's and du's identified on your handwritten work. Don't say you do it in your head. I want to see it. You know how to do it? Do it. Write it down. Maximize your points. You want max points? Good. We all want maximum points. So I claim this is going to be 1/3 sine of u, but for us, that's 1/3 sine of 3t plus some other constant. So what do we have so far? Let's do the intermediate step. And I do like to see intermediate steps on your work. Don't like skip and then go, bye-bye, ta-da, I got the answer. Oh, I did it all in my head. I'm good. And then I'm just going to not give you maximum points. Here's what you have so far. Your R of t, you took an antiderivative. Congratulations. You have arctan t plus some constant, C1. The comma, The middle component, we have 2 cos t plus some other constant, C2. The last guy was 1/3 sine 3t plus some constant, I have no idea, C3. So if you get that far and you have that on your paper and everything else was wrong, I give you a lot of partial credit because I'm just so happy that you show me these intermediate steps. I'm like, yay. Now what? Look at what the initial condition says very carefully. It says R evaluated at 0 seconds is going to give you the constant vector with components 1, -2, 3. Let me just write that down here because we're so far away. So this initial condition is telling me that R of 0 seconds better give me 1, -2, 3. Now, some students make the wrong mistake of going, oh, that's C1, that's C2, that's C3. And you could be right. But most of the time, the way I give quiz problems, I do it in such a way that that isn't going to be right. So don't do that. And I want to see the intermediate steps. When you substitute a 0 everywhere in place of your answer that you got so far, I want to see this step, like for realsies. Not hard. Just show me the intermediate step. You want that vector to equal the 1, -2, 3. Remember equality of vectors? So what does that mean? You can do equating components. That means arctan 0 plus C1 has to be equal to 1. That means I can equate the middle components. 2 cos 0 plus C2 has to equal -2. And then I also can be assured that 1/3 of sine 0 plus C3 for sure equals 3. Now go solve for C1, C2, C3, and then you can wrap up this problem and you're done. And we'll be done. And by the way, I'll stay late if anybody wants to go over any quiz problems. And also I have office hours today. You can come go over quiz problems. So does anybody remember what arctan of 0 is? If not, you can punch it up on your graphing calculator.
Is it 0?
Yes. 0 plus C1 is 1. Oh, good. We have C1 equal 1. Save that for later. Okay, how about cosine 0? Anybody remember what that guy is?
1.
Okay, so here, if I'm solving for C2, how about if I subtract 2 from both sides, I get C2 equals -4. Save that for later. And how about sine of 0?
Should be 0.
Yep. And that means C3 is just 3. So now you have your final answer. Final answer is going to be this vector valued function. I'm just making it really large. So R of t equals, here we go, arctan t plus 1. 2 cosine t minus 4. 1/3 sine 3t plus 3. Whew. Yikes. And there's your big final answer. Happy Friday, everybody.